This is Unit A Equilibrium continued. Next topic is the solubility products, which is represented by KSP, and it is for ionic compounds dissolved in water, which have low solubility. And higher the KSP value, the more soluble the compound. And for example, for calcium carbonate, which is in solid state, dissolving in water, producing calcium ion and carbonate ions. The KSP expression will be the concentration of calcium ion times the concentration of carbonate ions. And you see that calcium carbonate is left out of the expression because it is solid. And for PbCl2, lead chloride, it is becoming lead ions and 2 chlorine ions. And for KSP, it will be lead ions times chlorine ions squared because of this coefficient of 2. And if Q is greater than KSP value, it means there are too many products, which are ions in this case, because solid is dissolving in water producing ions. Because there are too many ions, it will proceed to the left and precipitate the solid will form. And if Q is equal to the KSP value, it means that the system is at equilibrium and it is the saturated solution where it contains both solids and ions continuously becoming each other. And if Q is less than KSP value, it means there are too much solids or the reactants. So it means that the solution is unsaturated and proceeds to the right to produce more ions. We have an example here. KSP for PbF2 is 3.6 E -8 at 25 degrees Celsius. Find the maximum molar concentrations of the ions, both of these ions, and the molar solubility in grams per liter. So first, we write the equation. Lead fluorine will become lead ions plus 2F minus. So KSP expression will be concentration of lead ions times the concentration of F minus squared because of this coefficient of 2. Now we have to assume that the concentration of Pb2 plus is S and concentration of F minus is 2S, because from this expression we know that concentration of fluorine ion will be as twice as the concentration of lead ions, and then square root of 2S. So this will equal S times 4S squared, which is 4S cubed. Then we know the value for KSP, which is 3.6 E -8, and that will equal 4S cubed. Now you solve for S, which is 2.1 E -3, and now we know the concentration of each ion, which will be the first part of the question. It will equal S, which is 2.1 E -3 molar. And for fluorine ions, it will equal 2S, which is 4.2 E -3 molars. And then for the molar solubility, it will just literally be the S value. And because S value will be in molar, we'll have to convert that into grams per liter. So molar solubility will be moles per liter. Then in order to convert moles to grams, you have to multiply this by the molar mass, which is 254.2 grams per mole. And moles cancel each other. Then you get the molar solubility of 0.51 grams per liter. And then the second question asks to find KSP value for saturated PbCl2 solution if Cl minus equals 0.0325 molars. And then we write the equation. lead ions plus 2Cl minus. And then KSP expression will be times Cl minus squared. And we know that the concentration of Cl minus will be 2S because it will be twice as the concentration of lead ions. So we know that the concentration of lead ions will be S, which is 1/2 of the concentration of chlorine ions. So it will be divided by 2. And now we can calculate for KSP. Concentration of lead ion was 0.0325 divided by 2 and times concentration of chlorine ions squared. And we get the answer of 1.7 E negative 5. And that will be our answer. This is continued from the previous question, and it asks, will it precipitate if 200 milliliter of 3.78 E negative 2 molar NaCl and 100 milliliter of 2.45 E negative 2 molar PbNO3 are mixed? So we know that the reaction will be NaCl plus lead nitrate will be NaNO3 plus PbCl2. So we know that it will produce PbCl2, which we talked about in the previous question. So it's asking, will it precipitate? So now we have to find the value for Q to find if it will precipitate or not. So if Q value is larger than the KSP, which we got in the previous question, which was 1.7 E negative 5, if Q is larger than KSP, it means there are mostly products at equilibrium, and products in this case are the ions. So if there are more ions, it means it will precipitate. So we have to now check if Q value is larger than KSP. So Q will equal same as KSP, lead ions, times Cl minus. And now we have to find the concentration of both of these ions. First, you have to find the number of moles of Pb2 plus and Cl minus in each of this compound. And then we have to find the concentrations of both of these ions in the mixed solution. So first, for the moles, you have 3.78 E negative 2 molars mole NaCl, so Cl, in 0.200 liters of solution. Then to find the moles of Cl minus, you have to multiply these, so you get 7.56 E negative 3 moles Cl minus. And in order to find the concentration of Cl minus, you have to divide this by the total volume of the solution. Total volume in this case will be 0.200 plus 0.100 liters. And that equals 0.0252 molar Cl minus. And we just found the concentration of chlorine ions. In same steps, we have to find the concentration of lead ions. So you had 2.45 E negative 2 molar of lead ions in 0.100 liter solution. And by multiplying these two, you get 2.45 E negative 3 moles Pb2 plus. Now you have to find the concentration, which you have to divide the number of moles by the total volume, which is this and you get 0.00817 molar Pb2+. And now, since you have both concentrations, you can now calculate for Q. Q equals 0.00817, the concentration of lead ions, times 0.0252 squared, which equals 5.19 E negative 6. Now we compare the value for Q with the value for KSP, which was 1.7 E negative 5. And we see that Q value is less than the KSP value. Because Q value is less than KSP, we know that it will not precipitate. Because in order for it to precipitate, Q value has to be greater than KSP. But Q is less than KSP, which means the solution is unsaturated and it will not precipitate. No, it will not precipitate because Q is less than KSP. This is the answer with the justification. That is the end of the video. Thank you for watching.